All right. So last time we talked about Kepler's three laws, and I hope you guys went and watched the Kepler. No, I didn't get a haircut. It's just tied. Um, I hope you guys went and watched the Kepler's law or the Kepler's Kepler documentary because it's really good. But we're going to continue with Kepler's law today. So we talked about what the Kepler's laws were last time. We're actually going to give some sort of mathematical explanation this time. So we're going to start over again from Kepler's first law, and then we're going to justify it, or at least give some mathematical backing, and then we're going to do the same thing for Kepler's second and third law. So let's go back to Kepler's first law. So remember that Kepler's first law is that objects orbit in enclosed ellipses. So the question that we can answer, though, it's a little bit harder to answer, harder to fully explain Kepler's first law, but we can at least answer the question, why are the orbits closed? As in, why do they repeat over and over again? Why don't they just like do this? Like, why do they have to overlap with themselves? Why do they repeat? So that's a question that we can answer. And so remember, when we say an orbit is closed or an orbit repeats itself, that means that every time the orbiting object makes or displaces an angle of 2 pi, it goes around a full 2 pi, it shows back up at the same place with the same speed and this, or with the same, at the same place with the same velocity. That's what we're going to try to show. So here's a quote unquote proof that that happens. So we're going to use Newton's second law to do this, to prove that this is the case. And so we're going to write Newton's second law in a funny way. So we're going to imagine that we have two orbiting bodies. One of them is fixed in place, has mass m1. One of them is orbiting around the fixed one with mass m2. So Newton's second law would be that the gravitational force g m1 m2 divided by r squared times r hat, that's the vector, this is equal to the mass times the acceleration of the second body. So this would be m2 times dv dt. So dv dt is the acceleration. We're just writing it in this way. So now we're going to use the chain rule. We're going to use the chain rule in a way that you guys probably haven't seen before. We're going to write dv dt as dv d theta dt. Kind of a strange thing to do, but I promise it'll be useful. And so what we end up with then from Newton's second law is we have m2 times dv d theta dt equals minus g m1 m2 for r squared r hat. And so now we're going to reach back to like last week, I think, when we talked about, or maybe it was even early, no, I think it was last week, when we talked about central forces. So remember that a central force is a force where the force points towards a particular place in space. And so gravity is a good example of that. Assuming that your two orbiting bodies are spherically symmetric, then the gravitational force pulls towards the center of mass of those two objects. In particular, if one of them is fixed in place, it'll pull towards the fixed object. And so when you have a central force, that central force produces no torque about that central point. Central forces produce no torque. And if they produce no torque, what that means is that, again, measured relative to that central point, that means that the angular momentum is conserved. And we call, in this context, we would call a conserved quantity a constant of motion, i.e. it's something that doesn't change regardless of how the actual object continues about its motion. It's the same thing. So like kinetic energy would be a constant of motion, assuming that energy was conserved in whatever system we're interested in, because it stays constant for the entirety of the motion. Right, so if the angular momentum is conserved, we can actually just write it down for any point of choice. So in particular, here we have angular momentum of an orbiting body. And by the way, the picture is like, you have your m1 here, and then you have your m2, say, going this way. This distance here is r. So we're finding the L of this m2. So the distance that it is from the axis of rotation is just, well, okay, let me rephrase. So this is just to say angular momentum is just I times omega. Omega is the rate at which it goes around, and we're just going to leave it as omega. It might depend on time. In fact, it does depend on time. It covers more angle here than it does over here, but that's neither here nor there. And the moment of inertia of an object, a distance r from the axis of rotation, is mr squared. So here, L, which is in this case I omega, would be m2 r squared omega. And omega, by definition, is the rate at which you cover an angle. So this would be m2 r squared d theta dt. Okay, great. So we can actually solve for d theta dt in this equation for L. We can rewrite d theta dt in terms of L. L is a constant of motion. To plug that into Newton's second law. Let me actually not put that there. So what we're left with after solving for d theta dt in terms of L is we have m2 times dv d theta times L divided by m2 r squared equals minus g m1 m2. We assuming these are point masses? Yeah. Well, so for the as far as gravity is concerned, if the objects are spherically symmetric, that's all that matters. However, as far as angular momentum is concerned, yeah, we have to assume that these are point masses, and really the angular momentum of the orbit is much, much, much larger than the angular momentum of the object rotating about itself. So we can neglect that for now. Right, so this is minus gm1 m2 over r squared times r hat. And so we can just do some cancellation, right? So m2 is going to cancel with m2, r squared is going to cancel with r squared. So what we're left with is dv d theta equals minus minus g m1 over L. Sorry, m1 m2. That was right. Yeah, it's minus g m1 m2 over L. Remember, L is the angular momentum here, times r hat. And now we're going to do something strange. So r hat is the unit vector that points from our origin, say, to the object. It doesn't get to the object, it's just a unit vector, but we can characterize that in terms of x, say x and y coordinates, right? R hat depends on the angle. So in this case, it's just cosine of theta I hat plus sine of theta j hat. It's just the standard unit vector. It points in a direction depending on the angle. Is that meant to be off center? You mean the axes? I just chose some random choice of axis, that's all. It doesn't matter, you can characterize it however. The value of theta doesn't matter, it's just how theta changes that we care about. And something to observe here is that this thing in front of r hat, this is just a constant. It depends on the mass, depends on the Newton's constant, and it depends on the angular momentum, but it's just a number that stays the same regardless of where the object is in the orbit. If it's here, it's always the same number. And so what we can do is we can just replace r hat with cosine theta and sine theta in the appropriate directions, and then just do an integral to get the velocity. So by doing an integral, it actually is relatively straightforward. We get that the velocity, and this is as a function of angle, by the way. So this tells us what the velocity is at different angles along the orbit. This is equal to minus, we can factor out the constant factor, gm1 m2 over L, and then we just integrate r hat. Well, integrating r hat, the integral of a cosine is a sine. So we have sine theta I hat, and then the integral of a sine is a negative cosine, so minus cosine theta j hat, and then we just have to add a constant. In this case, it's a constant vector because we would add a constant to this integral and add a constant to that integral. But it's just some constant vector. Doesn't matter what it is. And so now we can check. What happens if we plug in v of theta plus 2 pi, i.e., if you let theta go all the way around once, how does the velocity change? Well, the only things that depend on theta don't change when you go from theta to theta plus 2 pi. So this is just equal to the velocity at theta, i.e., the velocity vector is the same after you've gone around 2 pi as it was before you went around 2 pi. So that indicates already that something is repeating itself, i.e., the velocity vector isn't different Yeah, there is supposed to be an m2 there, and that's because it's that m2. The velocity vector could have been different. Like, for example, if it went like this, so by the time it got here, actually, no, let me redraw that. If the orbit did something like this, right, then these, this angle here, some angle theta, could have had a velocity vector pointing that way or a velocity vector pointing that way. The fact that the velocity vector is the same means it's traveling in the same direction at that, every time it goes back to that same angle, it's always traveling in the same direction. So we're not quite done yet. Oh boy. So using this result, that the velocity is the same regardless of how many times you've gone around, this tells us that the square of the velocity is the same. Right, and that's just kind of obvious to begin with. The square of the velocity is the same because the velocity is the same. But the square of the velocity depends on the kinetic energy depends on the square of the velocity. So the kinetic energy at an angle theta is the same as the kinetic energy after it's gone around 2 pi. And then we can use energy conservation. Gravity is conservative, which means that its potential energy, and indeed it must have a potential energy, its potential energy depends only on its position. And if the potential, how do I want to phrase this? Gravity is conservative, so it has a potential energy. So we can actually just write the change in, we can just write the energy conservation law using the change in kinetic energy and the change of potential energy at different angles, at theta and theta plus 2 pi. That is, so we have, that is kinetic energy of theta plus 2 pi minus kinetic energy of theta plus potential energy of theta plus 2 pi minus potential energy of theta equals 0. This is just energy conservation, just using theta 1 and theta 2 as our initial and final positions. Sorry, theta and theta plus 2 pi. These are 0, they're the same, right? Which tells us that the potential energy at theta has to be equal to the potential energy at theta plus 2 pi. But now our argument's done, because the potential energy only depends on position. So if the potential energy is the same, then the position is also the same. And so if the positions are the same, that means summarizing everything, the velocity is the same after you've made after you've traveled through 2 pi radians, and the position is the same after you've gone through 2 pi radians. That just means that you're going to keep repeating it over and over again, and hence you have that the orbit is closed. Because if the velocity is the same and the position is the same, how could you get something new after you do another revolution? And you could keep doing this 2 pi, 4 pi, 6 pi, and so on forever. You will always get the same thing after a full revolution, which gives us Kepler's first law. It doesn't actually prove that they're elliptical. That takes a little bit more work, work that we don't have the tools to do here. But it does show that the orbits are closed, that they will repeat themselves. Now, just as a quick note here, let's think about what had to work in order for this demonstration to work out. We had to have, so the thing that happened here is that we were able to do this integral because this number here was a constant. And so we could just integrate the r hat. But what if it wasn't a constant there? What if the gravitational force didn't go as 1 over r squared? What if it went as 1 over r cubed? Well, if it went as 1 over r cubed, then these wouldn't have canceled. And if those hadn't canceled, then we would have been left with, say, an r down here. And then we wouldn't have been able to do this integral, and we would not have necessarily gotten a closed orbit. So in fact, in order for, so it's very special that we have closed orbits, because it didn't have to be that way. If gravity was a 1 over r cubed law rather than a 1 over r squared law, then we wouldn't have gotten closed orbits. It just wouldn't exist in our universe. And then there probably wouldn't have been any life, because life probably needs closed orbits to work, or to arise rather. So it's very special. No, it's not. It doesn't necessarily imply intelligent creator. What it does imply is it does imply that the universe that we live in is special. And by the way, the fact that gravity is a 1 over r squared is actually derivable just from some first principles. And again, we can talk about that at a later date if you guys want to, like after lecture. But basically, this is saying that gravity had to be 1 over r squared. Now, just as a quick aside, we can do some calculations to actually relate the angular momentum to the gravitational parameters. So a useful formula for angular momentum is that L squared, this is for gravitational, L squared is equal to A is the semi-major axis, times 1 minus E squared, E being the eccentricity, times G capital M little m squared, where capital M is the mass, is the mass of the fixed body, and little m is the mass of the body that goes around. This is a convenient formula. And then we can just substitute this into the formula for r. R is a function of theta. Remember, r is a function of theta for an ellipse. We had a particular formula for it. That formula was 1 minus, or a times 1 minus e squared, I think, divided by 1 minus e cosine theta. I'm just pulling it up because I don't remember it off the top of my head. I wrote it down somewhere. Yeah, a times 1. Yeah, I got it right. Okay, yeah, it's so remember, r of theta is a times 1 minus e squared divided by 1 minus e cosine theta. So we can substitute in 1 minus e squared into this equation just to simplify, to write the orbit in terms of angular momentum. And we get that r of theta is L squared over g m squared times 1 over 1 minus e cosine theta. Which is just to say, if you increase the angular momentum of a system, the radius increases as the angular momentum squared. That's all. And that's assuming you hold everything else fixed. So this is a useful formula. You guys don't have a homework assignment on this, so you're not going to actually use it on a homework assignment, but it is convenient, and it's a useful way of understanding orbital mechanics. All right. Let's talk about Kepler's second law. We're going to do the mathematical treatment here as well. So Kepler's second law, just a quick reminder, is that an orbit sweeps out equal areas in equal times. This is that picture where we have this area, say A2. This is delta T2. And this area, say A1 and delta T1. So if A1 and A2 are equal, then delta 1 and delta 2 are equal. Yeah, the squared only applies to the orbiting mass, yes. So this was Kepler's second law, so we can actually give another mathematical formulation here. So I'm going to zoom in a little bit. Draw, oh, ugh, that's terrible. Actually, I'm not going to zoom in, I'll just draw it here. So let's say that, no, I will. So to examine this, it's actually really hard to do this at a finite scale, meaning it's actually really hard to compute the area of these wedges. So instead, we're going to do infinitesimal calculations and show that the infinitesimal result implies the finite result. And when I say really hard, by the way, I mean like you'd have to solve elliptic integrals. So none of these are true because they all require ideal scenarios, but they're true in the sense that we've used them to get rockets to various planets. They're true enough. So here's our picture. We'll put our focus here. So let's say that we want to find the area swept out for this itty bitty baby triangle. That's supposed to be a very small angle. Call it d theta. We'll call this distance here. This distance is r. We'll call the bottom one, it's slightly further away, so we'll call it, how do I want to do this? Yeah, so this distance will be r plus dr. So let me just put a little line there to indicate that's supposed to be a circle. Let me zoom in a little bit. So it's supposed to be like a curve. So this distance would be dr, and then because these are assumed to be the same length, this would also be r, this would be dr. And so this circle is supposed to be the circle that would connect up the whole thing, right? It would be this circle. That's what that little arc represents. Represents a segment of that arc. Right, okay. So let's proceed. So that distance is dr. Now, how long is this segment of circular arc? Well, you guys know how long you guys know how to do that. You guys know how to find the length or the arc length for a given angle. If this distance is r and the angle is theta, then the arc length would be r times theta in radians. So this distance, that little arc, is r times d theta. So now we're going to do what we always do in calculus, and that's just make approximations. And then because we're working with infinitesimals, it's good enough that we can just use these, we can just treat all squares of infinitesimals as 0 and treat all linear infinitesimals as infinitesimals. So what is the area of this whole triangle? Let me go back to using red. We want the area of this whole thing. We want to see how that area changes. The whole section on gravitation is non-definable, right? So the area of the triangle would be, say, dA, because it's a really small area. And by the way, the triangle technically does have curved sides, so it's not really a triangle, but it's close enough to a triangle, right? Like here, the picture that we're looking at is like a triangle that looks something like this. Like, yes, it has curved sides, but the curves are very, very slight because the angle is very, very small. So the area would just be the area of the two smaller triangles. It'd be the area of the triangle before the r d theta and the area of the smaller triangle after the r d theta. The area of a triangle is 1/2 times base times height. So the first triangle would be 1/2 times, what's the base? Well, the base has length r, and the height has length, or the height is r dr. It's a right triangle right here and there. And then the second triangle is 1/2 base, which is dr, plus height, r dr, or sorry, that's r d theta. Okay, great. So the rate of change of that area, how that area changes with time, meaning how that area changes if you have the same duration chunk at different places, well, we can just divide through by dt. So it's 1/2 r squared d theta dt plus 1/2 r dr d theta dt. So now what we would normally do, as we would in calculus, is we just take the limit as all of these things go to 0. And if theta goes to 0, then dr is going to go, or if d theta goes to 0, then dr is going to go to 0, and also dt will go to 0. Like if you do it over a 0 length time, then the angle spread out has 0 radians, and then the difference in distance is also 0. So all of these things go to 0 at the same rate. So here we have dr, dt, and d theta go to 0. And so in that case, d theta dt is still just finite. It's just a number. It's just the rate of change of theta. But r dr d theta dt is a number. This is finite. R is a number, also just finite. But dr just goes to 0. So in that limit, we have that dA dt is 1/2 r squared d theta dt. The last term drops out is what I'm getting at. And d theta dt is just the angle omega, or it's just the angular speed. It's the rate at which the thing passes through. So this is 1/2 r squared omega. And so we can multiply and divide by m. So we have m r squared omega divided by 2m, which is just equal to, well, mr squared omega is the angular momentum. So this is just L divided by 2m. And this is a constant. L is a constant, m is a constant. So that this is to say the rate at which, the rate at which you sweep over area with respect to time is constant. So regardless of where you are on the orbit, you're sweeping over the same amount of area per unit time. We can even just check that just by basically just doing the integral. So what we have that dA is equal to L over 2m dt. L over 2m is a constant, so we can literally just integrate both sides. And we're left with the area swept out in some amount of time is equal to L over 2m times the duration over which you sweep out that time, which just says that the area is always proportional to the amount of time, regardless of where you are in the orbit, which just means that two parts swept out in the same amount of time will have the same area. So Kepler's second law, also true. Now, something to note here is we did not have to use the fact that the gravitational force goes as 1 over r squared. In fact, we didn't even have to use the fact that it was an ellipse. All we had to know is we just had to know that angular momentum was conserved. That's it. And that gave us this property. So this is special because Kepler's first law required that gravity had a certain relationship with distance. Kepler's second law does not require that. All right, Kepler's third law is the last one, and perhaps the most, or the least obvious, most challenging maybe. So we're going to do the Kepler, or the mathematical treatment again. And remember, Kepler's third law was the statement that a cubed over t squared is constant for any given central orbiting body, which just says that if you increase the semi-major axis, you increase the period of orbit by a factor given by this relationship. So we're going to check this. We're going to check this for circles first. So the simplest orbit will be circular orbit. So let's check it for that, and then we'll move on to ellipses. So in a circular orbit, things going around at a constant rate. And that has to be true from Kepler's second law, right? Kepler's second law tells us how the speed relates to the angle. And so how the speed relates to the distance. So if the distance is always the same, the speed will always be the same. And so we can actually just find the speed in terms of the period by just dividing the distance covered by the time. So this would be 2 pi r, where r is the radius of the circular orbit, divided by the period. Now Newton's second law gives us the following. Gives us that the magnitude of the force, gm1 m2 over r squared, is equal to centripetal, the centripetal, or the mass times the centripetal acceleration. Because you're going in, it's circular motion, so the acceleration of the object is the centripetal acceleration. So this would be m2 times ac. Now m2 times ac is just m2 times v squared over r. And so v squared over, these should be capital R's because this is the radius of the orbit. And so we can just solve for v squared here. And we get that v squared is equal to g m1 over r. Okay, great. So we're going to combine this result, that the average speed, or that the speed is 2 pi r over t, with this result, which tells us that the speed squared is gm1 over r. We have that 2 pi capital R over t, all squared, should be equal to gm1 over t. Sorry, gm1 over r. And so we can just rearrange this, and we find that r cubed divided by t squared is equal to gm1 divided by 4 pi squared. And this over here, this is just a constant. It's just a number that depends on the mass of the thing that's being orbited around, exactly as we expected from Kepler's third law. And importantly, this r, that is the semi-major axis for a circular orbit. The semi-major axis and the semi-minor axis become the same thing. They both become the radius of the orbit when your orbit is circular. So this really is saying that a cubed over t squared is a constant. And in fact, it tells us what the constant is. It's gm1 over 4 pi squared. It's just a number. So now we have to do a little bit more work for ellipses, but we can still do it. So what we're going to have to do for ellipses is we're going to have to apply Kepler's second law, and we're going to have to use the area of the ellipse. So the area of an ellipse is the following, and maybe you remember this from geometry, maybe not, but it's just pi times AB, where A is the semi-major axis, B is the semi-minor axis. Kepler's second law is the following. It's that the area swept out, and this is what we just derived, is equal to L divided by 2m times delta t. And so actually, we can relate the area of an ellipse to the angular momentum, because if we sweep out one full orbit, i.e. if delta t is the orbital period, then the area we will sweep out is the full area of the ellipse. We then find that that is pi AB is equal to L over 2m times the orbital period, which is great because now we have the orbital period and we're relating it to some orbital parameters. In this case, we have A and B, and we don't want B. We want to relate the orbital period to the semi-major axis alone. So now we just have to use a little bit of geometry, which you may not know off the top of your head. This is just a geometric fact about ellipses, that B squared is equal to A squared times 1 minus E squared. It's just a fact. You can go home and check it. And so we can plug that in for B. So rather, we can square this whole thing and then plug that in for B squared. And we get that pi squared A squared times A squared 1 minus E squared equals L squared over 4m squared times T squared. I just squared this whole thing, and then I plugged in B squared is equal to A squared times 1 minus E squared. Okay, I know this is a lot. We have another step. Remember when I gave you the formula for L? It was L squared is related to the semi-major axis. That was like 10 minutes ago. L squared was A times 1 minus E squared times G big M little m squared. And so we can actually replace this 1 minus E squared with stuff that involves L and A and GMM, right? So that's what we're going to do. So then we're left with pi squared A cubed L squared over G M squared equals L squared over 4 little m squared T squared. And now the L squareds cancel and the m squareds cancel. And what we're left with after all of this algebra is A cubed divided by T squared is equal to G capital M over 4 pi squared, which is again a constant. And it's in fact, it's the same constant that we had before, gm over 4 pi squared. Here it's gm over 4 pi squared. I just used capital M here instead of little m1. So this demonstrates using Kepler's second law that that Kepler's third law holds. Now, just as a quick reminder, this result relied on the fact that the gravitational force is goes as 1 over r squared. That fact requires that statement. And so Kepler's third law also relies on the 1 over r squared property of the gravitational force. That's also necessary. It's just kind of hidden away in this equation. So that's the math, or at least that's some math, some basic math for Kepler's first, second, and third law. Now for something completely different. Actually, I think we're just gonna, I was gonna talk about gravitational potential energy, but I think that we're just going to not, because we're just not gonna make it that far. and we may as well end 5 minutes early on the last lecture. So I'm going to end recording here, and I'll open it up to questions.